The topics I'm going to cover are somewhat varied. I've got a little selection here. I've got a historical section on Bragg, and I'll tell you who he is. He was a professor at UCL, was the interesting part. And then I'm going to talk about X-ray diffraction, and I'm also going to talk about user facilities, and then get into some of the details about how we use these synchrotron facilities to develop technology that is going on actively at the London Centre for Nanotechnology. So I didn't, last on the list, but it won't be the last topic, is the discussion of nano crystals and nanoparticles. Okay, so this, I'm told, is a week dedicated to science and technology. I'm not sure if that's true, and I'm not quite sure who dedicated it. But what I have found is that this is apparently going through UNESCO at the moment. They're trying to declare 2003 as an International Year of Crystallography. And the reason for this is that this man, Lawrence Bragg, came up with this very famous law of physics in 1913, and it will be the 100th anniversary of that next year. So 2013 is designated as the year of crystallography. Just to be brief about it, crystallography has revolutionized all of the physical sciences, biological, chemical, and physical, and has led to something like 10 Nobel Prizes over the time since Bragg discovered this law. So it's really quite important for probing the structure of matter. So this is the only equation I'll show in the talk, but basically the idea is this equation represents the fact that if you have atoms inside your sample, which might be a medical sensor or a piece of crystal or something, then the light that scatters from one atom can interfere with the light that scatters from the next one. And if you get the angle right, they will interfere constructively over here. And if you get the angle wrong, they interfere destructively and cancel each other out. And so Bragg formulated that as a connection between the spacing of the atoms in the crystal and the wavelength of the X-rays which are used. And this very simple formula, which is just an optical geometric formula, has been carried on through the 100 years since the discovery of this to discover the structure of all kinds of interesting things. And I've used it for 35 years in my own career to look at the structure of matter. So one of the things I'm going to try to do today is to explain how we can see the structure of matter using X-ray diffraction. This is not an example picked at random. This is a very, very important example from the 1950s, where Rosalind Franklin made the first measurements with X-ray diffraction of DNA. And this led to the structure of DNA, which we all know of as a double helix. And here is the double helix as proposed by Watson and Crick in 1952. And the data that they used to get that information, which is about the structure of the gene, and very, very fundamental in science, that information all comes from this one photograph that was taken with X-rays on DNA by Rosalind Franklin in 1952. And I downloaded this picture from Wikipedia, I think. The total size of the picture is just 11 kilobytes, so it's a tiny little amount of data. But within this single picture is all of the information that tells you everything about the story of life, which is encoded in this DNA molecule. So, for example, the spacing of the base pairs which occur that contain the sequence of the DNA is contained in the position of this Bragg peak out here, which comes at a spacing, according to the Bragg law that I already told you, of 3.4 angstroms. And this X-shaped diffraction pattern in the center comes from the fact that it's a helical structure, and that was something that Crick himself was the expert on. And so they recognized it when Rosalind Franklin got this picture, that it was a helical structure. And then a fine point, but extremely important, was the fact that this spot over here is missing. So the fourth spot in the row is not present. And the only explanation for that is that it's not one helix, but two helices. And the two helices are offset from each other by 1/4 of the period of the helix. And that was interpreted by Watson as corresponding to two helices running in opposite directions. So all of those very important things for the copying of genes, those three facts, the base pairs on the center, the helical structure, and this double helix where the two, the parent and the child copy of the gene are actually built into the same structure, all comes from this one diffraction pattern. Okay, so I'm going to tell you about the Braggs. There's actually two of them, and they jointly got the Nobel Prize in 1915. So Bragg father and Bragg son, this was about their ages at the time when they got the Nobel Prize. Bragg father, William Henry Bragg, was born in Britain, a student in Cambridge, and went to Adelaide as a professor of mathematics. And Lawrence Bragg was born in Australia, and Australia is now very proud of him as a scientist, one of the most famous scientists from Australia. During their lifetime was the discovery of X-rays in 1895 by Röntgen, and immediately used, as I think many people know, to take X-rays of broken limbs so that you could repair them. And in fact, the very first patient of an X-ray machine in Australia was Lawrence Bragg, because he fell off his bicycle and he broke his arm. And the father had an X-ray machine and took an X-ray and took it to the doctor, and they figured out how to fix his arm. More importantly for this talk were the experiments that Henry Bragg started in about 1904. He'd trained as a mathematician and only got interested in doing experiments after a visit by Ernest Rutherford on his way from New Zealand to Britain to become a professor in Cambridge, first in Manchester, then in Cambridge. And the news about the X-rays was traveling very fast, but the properties of X-rays were really still being discovered. And one of the key steps taken by Bragg was to discover that you could measure the intensity of X-rays using the ionization property of the air. And so he developed these methods while he was still in Adelaide. And fairly shortly after that, he got a nomination from the Royal Society and came to take up a position in Britain, and a couple of years later ended up at UCL as the Quain Professor of Physics. And that was the same year that both Braggs got the Nobel Prize. And the prize was given for this discovery of Bragg's law, which is the thing that I just discussed. I also highlighted this because I was in Munich last week, and they were very proud of the fact that in March of 1912, was the actual discovery of X-ray diffraction itself, and that was done by Max von Laue, where they put a crystal into one of these X-ray beams and discovered that instead of the radiation coming out in every direction, it came out just in a few very specific directions, similar to these peaks that we're seeing over here on this diffraction pattern. And it was the Braggs who put their heads together and figured out why that was happening, and that was formulated as this Bragg law. So it was the combination of von Laue's experiment and the theory of the Braggs that led to this big breakthrough. Okay, so now I'm going to talk a little bit more about X-ray sources, because there's been quite a bit of progress in these over the years. So Röntgen's original X-ray tube was 1896. That's shown on this graph, which is a very expanded scale of brightness of source versus time. And what you can see is that for many, many years, everybody lived with similar kinds of technology to what Röntgen had come up with, which is just an accelerating voltage and an electron source and a target. And that was developed in Japan to a rotating anode source in around the 1970s. But what really took off was the development of synchrotron radiation. I'm going to tell you what that's all about. So here are two versions of the same curve, but notice the scale. This is going from 10 to the 10 photons per second in some units to 10 to the 34. So this is 24 orders of magnitude increase going to these free electron lasers, which people are playing with today. And this, of course, enables a great deal of new kinds of science. But it also has an interesting sociological consequence. Here is Britain's brightest light source. It's located somewhere between Oxford and Didcot and Reading and Newbury out in the west of London area. It's out in the country because the diameter of this machine is several hundred meters across. And it's a particle accelerator. The particles there are electrons running around in a circle inside here. I've got a second picture up here. Oops. Second picture here. So it's a particle accelerator storing electrons. They're running around in this direction. And they're accelerated to nearly the speed of light, 3 GeV, and running with a current of a couple of hundred milliamps. And every place where the acceleration takes place, to keep them in orbit, X-rays are generated and spilled off, and they come off as a tangential beam, which is then running down in the hallway outside this accelerator. And they've built something like 30 or 35 separate experiments inside this building that all look at that same source from a different angle. So each of them gets fed with a different beam. And you can see one of the long beam lines is coming outside the building here, and they're now built, but there are additional beam lines coming outside. This is the one that I'm currently planning to use, which goes up 250 meters away from the source. So there's a building out here now which is housing the experiments that are done here. Now, this kind of science doesn't come cheaply. This machine costs 350 million pounds to build. And the reason that that's cost effective is that it's shared by not 350 million, but some tens of thousands of scientists who come here. Roughly 5,000 per year are coming to do experiments, and everybody gets a few days on one of these 30 stations that you're able to do experiments on. But you get enough time that you can complete an experiment and then go home and publish it. And the big advantage for the users of the facility is that they don't have to maintain the lab themselves. They get to benefit from a professional team that runs it for you, and then you can do your experiment on that on that piece of equipment that's been built for you. And this is the meat of the machine, which is an X-ray undulator that produces copious amounts of X-rays shooting in a straight line that feeds an experiment. Okay, could I ask for the lights to be turned down, because I'm going to do a short demonstration here. Because of the cost and size of the machine, I can't bring a synchrotron to show you, but I can bring a laser to show you. This laser pointer, which is not particularly special, it's slightly brighter than a typical laser pointer. You can buy these on the street in Hong Kong for 100 Hong Kong dollars. So this has got far more coherent photons in it than that synchrotron that I just talked to you about. But the difference is the wavelength is 1,000 times longer, so the things we can look at are 1,000 times bigger. But I'm going to show you a couple of demonstrations of things that you can look at. So talking of Hong Kong dollars, Hong Kong's currency is better than British currency because it has a fraud detection panel in it. And if I shine the laser here through the plastic piece inside the money, you can see that there's a lot of structure that appears. And as I move it around, the streaks and spots all redistribute themselves. That's because it's diffracting from the hologram which has been inserted into this money as a fraud protection. While we're on the subject, I also have an Australian one which also works. And one day we'll have them. The Hong Kong one is better than the Australian one, but anyway. So these are holograms, transparent holograms, which are built into the money. And if we do a more sort of conventional experiment, I've got a small hole in a piece of metal here, and if I shoot the beam through that small hole, those at the front at least, and if the lights were to turn down, we would see that there's a couple of streaks, and if you look really closely, and if I stand back, you can see that the streaks are actually modulated with fringes, and this is the diffraction pattern of the slit. So the idea here is that the microstructure, which in the case of a laser is on the micron length scale, is accessible through this diffraction phenomenon that I'm just demonstrating here. And you can learn a lot about the structure of things. With light, you can look at micron scale. With X-rays, you can look at nanometer scale. And that's where the ability to look at the atoms inside a material comes from. So this is a piece of machined aluminium. The machinist who cut this used two different tools, and if I shine the light on this surface, you can see one kind of pattern, which is due to the tiny little grooves on the scale that the machinist cut the pattern. If I rotate the piece around and look at a different part, I get a different pattern because he used an end mill for this side and a fly cutter for this side. So you can see very clearly there's a big difference between these two kinds of machined surfaces, and it's a very straightforward thing to look at. But you can also just put it under a microscope and do it. Okay, well, where Bragg comes in is if we look at a regular object such as a crystal, and I can model that with looking at a grating, and if I put the grating on the screen, you see a lot of beams coming out. These are the Bragg peaks that come from the scattering from that lattice, which is inside the grating here, seen with visible light. And if I look at an even more exotic grating, then let's see what we've got here. I picked this one at random. We've got a pattern that somebody has engineered into that grating to make it look like an image. Now, there are no lenses in anything that I'm showing you here. This is just diffraction from a piece of plastic which is inside this tip here. And there's another one. You can see it looks like I'm projecting an image, but in fact, what the engineer has done is generate an object whose diffraction pattern is the man in the moon. So you can see that rather nicely. Now, to my trained eye, I've been working with diffraction for over 30 years. To my trained eye, I can actually read a lot into that pattern. The first thing that you'll notice is, well, I wonder what strikes your attention first. But what I notice first is the second moon and the third moon off above and below that are coming from the fact that there's a periodic array of moons that are visible there. You can also see that there's a faint backwards moon in the center because the moon is a very asymmetric object and the pattern is generating a ghost of the wrong orientation of the moon. And if you look really closely, you can see little pixels on the moon that are all coming from what has gone into the design of this little piece of plastic that is used here. Okay, so curiosity got the better of me, and I put this under the microscope. Here is a scanning electron microscope image of that piece of plastic, and here is a visible light image. And you can see it's got a lot of squares in it with a spacing of 5 microns, as I measured. And it's the 5 micron spacing here which gives the second and the third moon that I just showed you in that diffraction pattern. And what gives the pixelation is the fact that the pattern is repeated every millimeter on the piece of plastic that I put inside the beam there. Yes, I brought this one as well, but I just thought an everyday object like a telephone, if we just go back and look at that's got a diffraction pattern as well. So it's got a lot of little extra spots. That's coming from the pixels of the display of the telephone that I'm shining the beam on. So these are sort of everyday microscopic objects on the micron size scale that you can look at with laser light diffraction. So now I'm going to move on to X-ray diffraction. And everything I've said about structure and seeing the structure through the diffraction pattern applies to X-rays, but on 1,000 times smaller length scale. So here we have a piece of sample that might contain a lot of crystals, and if we shine an X-ray beam from the diamond light source onto this, then we will get a whole ring of peaks, and if we look at the peaks that come out, then you can see that some of these have got fine structure in them as well. And we can then extract this fine structure peak and perform a mathematical calculation on it called the Fourier transform and get an image of the particular crystal that was giving this Bragg peak. And you get a lot of crystals, and so you can go through one by one and look at all of these. And this is one of the things that I'm currently doing with our experiments at the Diamond Light Source, looking at objects such as this one. These are chemically synthesized nanocrystals of silver They're about 100 nanometers across. A nanometer, of course, is 1,000th of a micron, and a micron is about the smallest thing you can see, even with a microscope, using visible light. So this is really quite small. And these have got all kinds of applications in medicine and nanotechnology. But these are little crystals that are cubic shaped, and if we shine an X-ray beam on one of those, we get a diffraction pattern. This is just a calculated one, but it's a three-dimensional version of that shape transform that I just showed you with the laser. Now, Bragg in the 1930s, this is Lawrence Bragg, published a paper where he was trying to solve the question of how to go from this diffraction pattern to an image of the object. And there's a very important thing which is missing, which is the information about the relative phase of all of these different spots that come out of a sample when you look at it. But Bragg ignored that, and he just asked the machinist to drill a plate with holes in it with a size given by the size of the spots that appear on this on the film of the diffraction experiment. And then you could shine a laser, except there weren't lasers in 1936. You shine a bright light source on it, and you can replay that structure 1,000 times bigger, and you can turn it into real space, and you get an image of the crystal magnified 1,000 times by the change of wavelength. And this is a crystal called diopside that they were interested in. It's a calcium magnesium silicate that's very important inside the Earth's crust. And the correct answer for that pattern you can just calculate using the Fourier transform once you know the structure. And it's got the property that I showed you with the moon, that you have it's a double image with the correct image and the reversed image superimposed on each other. So it needs a little bit of unfolding in order to convert this into a structure. But this was a method that Bragg was working on in the 1930s. Now, today we use a computer algorithm that is just shown here. We take the diffraction pattern, this three-dimensional distribution of spots, diffraction spots, and we can invert it using the calculation to get an image of the object, and that's demonstrated here. Here's the diffraction pattern actually measured from one of these silver cubes. There it's shown as a movie scanning through the center of the Bragg peak. And this is the result of the calculation. You get a faithful image of the cube coming out. And you also get information inside this object because it's a three-dimensional image that you're getting. So you can then probe inside it and look at where the defects are and where the distortions are inside there. So the last thing I'm going to say is concerning medical applications. And I'll be a little bit brief here, but please ask questions if you would like me to give more information. What we've been making are gold nanocrystals about 200 nanometers across, and we make them on substrates, and they can be measured in the same way. We measure this diffraction pattern, and we can invert that diffraction pattern to get images of the three-dimensional images of the crystals, and we can see the distortions of the crystals through this phase information. So these things are then built into sensors, and this is the work of Rachel McHenry, my colleague in the LCN. Her academic department is medicine, and her application is to come up with ways that you can sense levels of sugar in the blood and things like this. So you have an immersed sensor which is running around inside blood serum, and you want to try to detect through nanotechnology, try to detect the concentrations of these chemicals. So the way that she does this is to take some linker compound which has some organic binding agent, such as an antibody on one end, and connect it through a sulfur atom to a gold layer, which is then attached to a silicon so-called MEMS device, a micromechanical readout device, which is a cantilever. And this cantilever is 1 micron thick, and when it has stress applied to its surface, it bends, and you can read out the bending using an electronic circuit. What we're looking at is the chemical interaction between these biomolecules and the gold. And that's the one experiment I'm going to tell you about in the last couple of minutes. So here's a magnified view of one of these gold films. You can see that it's made up of little chunks of gold that are about 200 nanometers across, if you care to measure them. And so our test crystal is a model of one of these grains here. And if you measure the bending of the cantilever as a function of deposition time of the sulfur-containing biomolecule, you get an interesting response here, which is spread out over many hours. So there's a slow reaction taking place. So we reproduce that in our beamline. This is done on one of these end stations of the synchrotron. And we take a sheet of these gold crystals and then apply the thiol through a syringe so that we don't disturb the sample or disturb it as least little as possible. And then we measure the diffraction pattern. This is showing as a function of time after dosing, and 1 hour, 2 hours, we get a small but distinct change of the diffraction pattern that we can then interpret in terms of the change of the pattern of stresses that's taking place inside the sample. So when you invert the diffraction pattern, you get this image showing a negative distortion of the top of the crystal and a positive distortion of the bottom of the crystal. So there's a relaxation of the faces of the crystal, and you can model it by finite element kind of calculations. But in order to get this pattern of distortion, you have to have a differential between the curved parts and the flat parts of the crystal. And that's what we conclude quantitatively from the experiments that are shown here. And what causes this distortion can be seen in other structures of gold, very small gold particles, where you have these gold-sulfur chemical structures that are forming. These only form on small particles, and so the conclusion then is that we've got one kind of reaction taking place on the curved parts of the crystal and a different kind of reaction taking place on the flat parts. And the differential between these is what gives this strain response that can be built into a sensor. So what you're seeing is a macroscopic response of the sensor to an atomic level chemical interaction which takes place between the biomolecule and the physical gold species that is the active components of the device. Okay, so a reminder, we're looking at 100 years of Bragg diffraction with a little bit of a celebration, at least amongst the people that care, next year, starting in Adelaide in December, I believe, of this year. I've told you a little bit about this mode of doing science using shared facilities, which is a little bit new and a little bit, it takes some getting used to, but it's actually a very cost-effective and strongly supported way of doing science, pros and cons, of course. I've told you a little bit about coherent diffraction imaging, which is what I spend most of my time doing, and the goal is to look at nanocrystals and to see how the shapes and strains depend upon their environments. And then I just briefly described how you can build that into a sensor that can detect a change of the chemical environment of a film of gold inside a liquid medium. So thank you for your attention. I welcome your questions.
Thank you very much. Any questions?
What are the big research
But there's a mic
questions?
coming.
Sorry. Really interesting presentation. Thank you. What are the big research questions now?
In which
this
branch
field.
of science? In nanotechnology? Or in...
No, in diffraction.
In
and
diffraction,
the structure
okay.
of...
Well, one of the questions, just because I was reading about it on the train on my way to do the experiment just the other day, is the structure of the minerals that go on inside the Earth. So one of the questions is what happens to minerals as you go down to thousands of degrees inside the Earth, and what structures they have. And that can be done rather nicely using a pressure cell, which takes a micron-sized piece of crystal from the Earth and compresses it to the pressures of the center of the Earth. And in fact, something I didn't know was that there was a new phase of magnesium silicate, the compound I was just talking about, was discovered that way. And it starts at 120 gigapascals, which is very, very deep inside the Earth. And this was done done by a group in Tokyo just recently. So that's one of the science questions, earth sciences. And then in the medical area, a big user of these facilities are so-called protein crystallographers who grow crystals of proteins, put the protein crystals in the beam, measure the diffraction pattern, and get an image of all of the atoms inside the proteins. This is probably 1/3 of the users of Diamond do just that one method. So those are two good examples.
Thank you. Any other questions? Yes, we have a couple in here.
Yes, I had to be brief on the technical side of that, but it's actually quite an interesting anecdote with Bragg, because Bragg knew this, of course, all along. And when he did that simulation by drilling holes in a plate in order to use light to generate the diffraction pattern, the next generation of that experiment was to put little plastic or mica slips over the holes to change the phase of the light going through to the correct phase that they'd actually discovered from studying the crystal structure. So they were actually able to put in that phase information into that calculation a little bit later on. In our method, we use a big computer that does iterative calculation thousands of times over, and it uses the fact that the diffraction pattern can be measured more finely than necessary, and the extra information in between the minimum necessary sample points contains that phase information, which can then be extracted.
There's another one.
What's information can Diamond Light give on materials such as amorphous solids? Is that something that's being looked at by them or the LCN?
Yes, absolutely. LCN, as it happens, not so much, but amorphous materials, they come a bit low on my list because they don't have this beautiful diffraction property, and it means that the crystallographic methods at least don't work very well. But there are many good diffraction methods which are perfect for looking at amorphous materials, and there's several of the faculty of the chemistry department that do this. There's a method called pair distribution function, which is alive and well for looking at amorphous materials, and that certainly works. But amorphous nanomaterials are not so interesting, let me say, but maybe I don't want to be quoted for that. But
Any other? Yes, we have one.
I can be loud, yes, I normally able to speak loud. I was just wondering whether the last device you showed us, this nanometric sensor, is it aimed at some specific medical problem, or is it just a general sensor that can solve a variety?
It is aimed, I believe, as a glucose sensor for measuring blood sugar levels continuously. Because, as you know, the standard medical practice is you take a prick and you measure the glucose 3 or 4 times a day. It's a little inconvenient, but you could actually attach or implant a sensor that would give an electronic readout continuously of blood sugar levels. I think that's the one that Rachel has in mind. Yeah.
Any other questions? It seems not. So I think we've finished for today, but I'm sure you'd like to join me in thanking Professor Robinson in the usual